In this video, we'll see how LC oscillators work and what their types are. This is how a general LC oscillator looks like. The feedback network consists of impedances Z1, Z2 and Z3, where Z1, Z2 and Z3 are reactive elements. This means they are either capacitors or inductors. We want to see how this circuit oscillates, so we need to find the loop gain. For that, we need to find the open loop gain of the amplifier and the feedback factor. We'll break the feedback loop to find the loop gain. We redraw the circuit as follows. Suppose the output resistance of the amplifier is R0 and the load impedance is ZL. ZL will be equal to Z2 parallel Z2 plus Z3. If the gain of the op-amp is AV, then at the output of the op-amp will be minus AV since the feedback input VF is fed to the inverting terminal. This will be further attenuated by R0 and ZL, the load impedance. Using voltage division, the gain will be minus AV, ZL upon R0 plus ZL. The feedback factor beta is how much of the output will be fed back to the input VF. Hence, using voltage division between Z1 and Z3, we have beta as Z1 upon Z1 plus Z3. Hence, the loop gain A beta will be AV into Z1 into Z2, upon R0 into Z1 plus Z2, plus Z3 plus Z2 into Z1 plus Z3. We consider Z1, Z2 and Z3 to be purely reactive components. Hence we replace Z1, Z2 and Z3 with JX1, JX2 and JX3. We get the following equation. Applying Barkhausen's criterion for oscillations, we need the phase shift of this loop gain to be 0. Hence, the imaginary part of this equation should be 0. That gives us x1 plus x2 plus x3 equals 0. Substituting this into the loop gain equation, we get the loop gain as AV into x1, upon x1 plus x3. We can replace x1 plus x3 with minus x2. We need the magnitude of this loop gain to be 1. Hence, the gain AV will be x2 by x1. Well, that solves this circuit. Let's take a look at the equation closely. As x1 plus x2 plus x3 equals 0, it means that at least one of x1, x2, x3 must be of a different sign than the other two. This means that either we can have two capacitors and one inductor, or one capacitor and two inductors. This gives rise to two configurations. The first is the Hartley oscillator. Here x1 and x3 are inductors and x2 is a capacitor. Here the values of reactances are x1 equals j omega L1, x3 equals j omega L2 and x2 equals 1 by j omega C. We substitute this in the two equations we derived for the general case. That gives us the following. Omega naught is equal to 1 by root L1 plus L2 into C. We can divide by 2 pi to get the frequency of oscillation in Hertz. And the gain AV is L2 by L1. The other one is the Colpitts oscillator. Here x1 and x3 are capacitors and x2 is an inductor. Here the value of the reactances are, x1 equals 1 by j omega C1, x3 equals 1 by j omega C2 and x2 equals j omega L. We substitute this in the two equations we derived for the general case. After doing so, we get the following. Omega naught is equal to 1 by root L1 C1 C2 by C1 plus C2. We can divide by 2 pi to get the frequency of oscillation in Hertz. The gain AV is C1 by C2. For LC oscillators, the op-amp should have a high enough slew rate and bandwidth to be able to produce the oscillation frequency without any distortion. Alternatively, we can use BJT or FET-based amplifiers instead of the op-amps. That's all for this video. If you have any doubts, feel free to ask in the comments section below. Don't forget to like, share and subscribe.